can also do.
Got to say for themselves. Good evening, panel. How are you doing?
Doing very well, thank you. Is that the Motley Q for the Motley Crew?
Oh,
oh dear.
Is that the best you can come up with, Dave, this time around?
Yeah.
At this moment, yes.
That's an
slowing down.
We've got a couple of Trump jokes, but we can't do them on the air.
No, don't do them. God's sake.
No, we're not going to do that.
Oh, dear. But yeah, in the panel tonight, we've got some of our usual suspects. We've got joining us tonight, and we've got John Thatcher from Shropshire Astronomical Society. Hi, John.
Hi there.
So, how's it going over there? Where are you in Shrewsbury, or is it more towards Shifnal?
No, I'm actually in Shrewsbury, or Shrewsbury, or Shrewsbury, or one of the other versions of the name.
Yeah. Yeah, so we got another Shropshirian. We got Darrell at the top, or Daz as we call him. He's another Shropshire lad. He's based. Is it Land?
Westbury.
Hey,
Westbury.
Westbury.
Yeah, just on the border of just about 9 miles from Shrewsbury. Yeah.
So we got in the chat tonight. We got Dave Galvin, Liverpool Astronomical Society. Hi, Dave.
Hello, everybody. Welcome to the show.
We got Andy, the astronomical correspondent for Astro Radio over there in Spain.
Hello, everybody. Welcome to the show. Thank you for listening.
And we got Mr. Simon Holbeach, the painting expert of Bath Astronomical Society.
The resident painter.
You've got to have skills. You've got to have skills.
The only bloke I know who just continued to paint through lockdown 1.
Hey, I've got permission to paint in lockdown 3.
Oh no.
Of course, we got Michael from Ghost Space Watch down the bottom.
Yeah.
So what we'll do is start off. Well, Michael, what you got anything to report with Ghost Space Watch? What you got coming up?
Yeah, we've got our postponed meeting next Wednesday. That was supposed to be done on the 6th of January. Unfortunately, I suffered a little accident at home, and I was out of action for that night. So I've postponed it till next Wednesday, which is the 20th. And it's the hunt for near-Earth objects by Gate 8 of the Space Guard Centre. That's what we got coming up on this Wednesday. And the following Wednesday, on the 27th, we have Dr. David Whitehouse talking about the next 50 years in space, based on his book, Space 2069. So, and all details are on the website, gospacewatch.co.uk.
Excellent. So, Simon, anything happening down at Bath?
We had Damon Peach talking to us last night, which is kind of fun.
Yes.
Yeah. I had one job to do, which was push the record button so that we could record it for those that couldn't attend, and I did it 3 minutes late. So other than that, success.
It all went well.
Yeah.
Is the Herschel Museum still closed?
It will be closed until probably the end of February. Yeah.
All right. So that's a shame, isn't it, really? But
I've got the keys, Pete, but you're not allowed to travel. But when you can, I've got the keys.
Aha.
Yeah.
There you go. And Andy, over in Spain, haven't you been deluged in snow over in Spain?
Well, a lot of Spain had, especially in the interior. You probably saw on the news that Madrid got it quite badly. But here in Catalonia, we seem to have evaded it, although there was one night, I think last weekend, they were forecasting it all night and we didn't get any at all. So we've been lucky, really. But I mean, I'm sure it'll come. I mean, we do have heavy snow quite regularly, so it will probably turn up this winter because it's turning out to be quite a cold winter so far. So we will see.
I've just had a message from Stefan in the Russian Republic. He says, tell Andy, he says he doesn't know what snow is till he comes and lives just outside of Moscow.
Stefan, you're definitely right there. But you can keep it. Thank you very much.
And Serge in India, he's in Chennai, something out of Star Trek, isn't it? Chennai. He's just sent an email in and he said, "What's snow?" We've had none here in Whittington. I don't know if you've had any over in Shrewsbury, John, but we've had none here in Whittington.
Had a bit the other week, but
no, we haven't either. No.
You know, because I mean, Kath can't be with us tonight. She's got an interview or something, so she's got to get prepared for it. But she was saying over in Shifnal they had quite a bit.
All right.
Yeah.
Yeah, she did post some pictures. It would look quite nice.
So, Dave, up in Liverpool with the Liverpool AS, you got anything coming up?
Yep. We have our monthly meeting tomorrow, Friday, tomorrow at 7 p.m. Details are on our Facebook group. It's the Northwest Space Strategy, and that'll be given by Alan Cross.
All right.
Should be very interesting. The details are on the Facebook. We're doing it out there on YouTube as well, so you'll be able to just sit there and watch it and enjoy it on your big television, maybe. Should be good, very interesting.
That'll be good. And John, you've got a meeting coming up this Saturday.
Yeah, this Saturday evening, Shropshire Astronomical Society. There's 3 of the members doing a 20-minute talk each. So Steve Swagian will be talking about what you can see in the night sky. I'm doing the first of what I call a series of 1 million on space travel, which is designed at a very basic level. So it's mainly pictures, very few numbers in it. But that's going to start off talking about traveling to low Earth orbit, effectively, to start with a plan to extend it to intergalactic travel, in due course.
Nothing like ambition.
And then Andy will be talking about what's to see on the moon.
All right.
Three sort of relatively short talks to people.
I'll be in at that meeting. Yeah, because as you know, the Shropshire Astronomical Society actually formed in this very house, in the front room, in the bay window of the front room. Many years ago, when I was young and I had hair and everything.
Was that before electricity came along, Pete?
Yeah. We used to bring in the candle and everything.
Pre-gasp.
How many candles?
Just the one. Sometimes we had 4.
Yeah.
That was when you got your new phone, wasn't it?
Well, it was heavy going on that window tax as well, wasn't it? So it was just the one window.
The window tax,
yeah.
Is there a plaque, Pete?
Yeah, there's a plaque on the front door saying, it's one of them blue plaques saying it started here in 1870.
Yeah.
Sponsored by Nokia.
Yeah. It's just taking the mickey out of my phone, John, because it's one of those Nokias from way back. One of well, it's a reissue of it, but it's still in the same style.
It's a retro model.
Yeah,
That's what it is.
Yeah.
It's a retro look.
I don't like all these apps and all this stuff. It drives me mad. So, John, apart from being with the Shropshire Astronomical Society, you also help out at, I believe, Cosford Air Museum.
Yeah, I'm a tour guide at Cosford, although obviously that's stopped at the moment. And I'm heavily involved with the Aeronautical Society, who also meet at Cosford. Yeah.
And also, I mean, for the listeners that won't know this, you were involved with a very, very famous telescope. So can you tell us a little bit about that?
Yeah, James Webb Space Telescope. I spent 10 years on that. I worked in the space industry for 30 years. And the first bit of that was really doing what you might call the bog standard communication satellites, things that in geostationary orbit. And then I got involved in space science. So I was the original project manager on Beagle 2 with Colin Pillinger in the early days when it almost died on several occasions because of doing it on a shoestring. And I've been involved in various sort of studies and things. And then I got involved with James Webb. And that was, I mean, it was one of those projects where at the end of it, you say, nothing will ever match this for interest and excitement and what it might find. Yeah. So I'm going to retire. And I was close enough to be able to do it. And so I retired in 2013 thinking that, it'll be launched in a few years' time. And I moved from the Far East, or Bedfordshire as they call it here, to Shropshire. And here we are over 6 years later, and this damn thing is still not off the ground.
No.
And the sad thing is, all the bits right at the beginning, I mean, and this goes back to the mid-1990s, it was the Next Generation Space Telescope. It was what it was known as, NGST.
Yeah.
And the bits that were identified as the biggest risk, of course, were the mirror, for one thing, because it's individual mirror segments made out of beryllium. You can't do a big glass mirror like Hubble at that size. You never get off the ground. So the mirror technology was one huge risk area. And in fact, there were 10 major development items on the project were identified as, you know, the biggest 10 risks. So it's technically an audacious project. I mean, it's a huge number of risks and things involved in this are horrific. And all the things that they were worried about were all sorted out. And what's really delayed it was the basic spacecraft, what we call the bus, the box, if you like, that powers it, points it, controls it, does the telemetry, all that sort of thing. The basic spacecraft bus that should have been dead straightforward is the thing that got screwed up. And I don't want to go and slander somebody here, but the some of the cock-ups that were made at a very large American aerospace company are just unbelievable. Some of the things that happened, I mean, totally unforgivable, quite honestly. And the project nearly got cancelled at least twice, with cost overruns and all the rest of it. So NASA will spend about $10 billion over the lifetime. You know, that covers not just designing it, building it, testing it, launching it, but then the operational period should be at least 10 years. On top of that, the Canadians have put in a significant amount of money, and the European Space Agency has put in about 500 million euros. Plus, the instrument I worked on, the mid-infrared instrument, was actually paid, it wasn't paid for through ESA. 10 European countries independently funded their bit. So the UK Space Agency, as it now exists, actually funded the UK share of this on top of the ESA contribution. So the total cost is, you're talking well over $11 billion at least. And they're pretty close to blowing that budget. If it gets delayed again, it's going to be a major issue. But nevertheless, I mean, the work, the most amazing work, a huge international team, and the discovery potential is just enormous. And as the astronomers say, it's not the things we know we're going to look at that we're excited about. It's what we're going to see that we just didn't expect. And it's going to be, what the bloody hell is that? You know, how do you explain this? That's what the astronomers get excited about. But for me, I mean, I'm an engineer by training, and you know, after a while, they end up making you project manager because you need to be a bit past it for engineering. But actually working with professional astronomers for that period of time was a fantastic opportunity. And we have regular meetings moving around Europe because the whole job was run off basically email and voice, you know, phone calls on speakerphones, and we'd have, you know, quite often phone calls with at least a dozen locations all around Europe, and sometimes we tie in America as well. So one way of keeping it all together was to have physical meetings every few months, and we tend to move around the European sites. So you're going to have a 2 or 3 day session, and in that there's always some social activity. And there'd always, you know, it's mainly sort of working meetings, but there'd always be a session where we get the astronomers to give a talk, what we said, do it for engineers, so we can kind of understand what you guys are talking about. And inevitably, most of the astronomers left the engineers behind because they're used to chucking up log graphs one after the other. The engineers are sitting there trying to work out what the axes are, and they've moved on to the next one. But you kind of got the gist of what they're on about. So it was all his own stuff. I mean, that's what I used to say to people. You know, my career was basically satellites, rockets, and the physics of the universe, and I got paid for it.
You can't get better than that. I think one of the most, it wasn't comical at the time, but I don't know if you put your mind back to when I came over to Shropshire to do the talk on remote telescopes, and that guy got up and gave me a really hard time.
Yes, I remember it well.
Yeah, and it was getting a bit heated, was it not? Yeah. And the funny thing was that he was sitting next to you, and I'm thinking, you're sitting next to the bloke that's involved with the most remote telescope you're ever going to get. And he was looking around trying to get this argument. And I remember this fellow, it's Stan, is it Stan, his name?
Stan, could well have been Stan, yeah.
Who used to do the observing sessions over at the
Stan Courtney,
yeah. And I expected him to be dead against it, but he actually jumped to my defense. And I thought, I can't even believe that Stan, who's never even probably seen a camera, has just jumped to my defense. And his best one was, how do you turn your television over, mate?
Yes, that's right. Yeah, that was a good one.
Yeah, but the last time we met was over at the castle when we did that session. We did that astronomy session over at the castle.
Yeah, that's right. Yeah,
over the road. That was good fun. And of course, we had another one organised, and yeah,
Wallop.
And here we are, Wallop. Yeah, so I'll open it up to the guys to ask you any questions they'd like to ask you.
Just my thoughts is we get told that this is the successor to the Hubble Space Telescope, but it's in a different league, isn't it? It's viewing the universe in different wavelength than the Hubble.
Yeah, well, the thing is,
we're going to get new stuff. We're going to get new information.
Yeah. I mean, Hubble can only look back so far. When they started, they thought, Hubble would be limited. But what happens with all these telescopes and science instruments and space is you learn how to operate them, how to tweak them, how to get more out of them. The software improves and all that sort of thing.
Yeah.
So Hubble can look back about 10 billion years. The problem is, if you want to look back further, because of the expansion of the universe, the actual fabric of space-time expanding, the wavelengths of stars, which all tend to be, they're all sort of hot bodies, it's the peak wavelengths tend to be in the optical or close to it. But because these very old objects are so far back, the expansion of the universe has literally stretched the wavelength of that light. So if you want to see and get data from those early objects, there's no point in looking in the optical. You won't see it because all the key information is moved into the infrared. So they knew they had to build an infrared telescope. Here's a little aside for you. I can remember very early on, I think I joined in 2004, and NASA they were getting some publicity together, and they got a tagline. They said, and it wasn't, just be decided to be called James Webb. And they said, I think their tagline was something like, the first light machine. And they were dead pleased with this because it was like a play on words. It was either the first light, as in the first stars and galaxies, or the first light machine, However, within a few years, it was realized with the discoveries being made that actually the first stars may be even older than we thought. And now you've got to be very careful. James Webb probably won't be able to see the very first stars. It might see it'll see the first galaxies possibly, and it'll be the first supernovae in those galaxies, but actually detecting the very first stars might even be beyond James Webb.
Yeah.
But this is just a way, an example of the way things have moved on. But you have to make it to operate in the infrared, which means it's got to be cold. So the first thing that tells you is you can't put it in orbit around the Earth.
Yes, yeah.
Hubble's at about 500-600 kilometers up. The Earth is a big ball at 300 degrees Kelvin, or roughly room temperature, if you like.
Yeah.
And that close to it, you can't keep a telescope that cold unless you've got a huge supply of cryogen, and that's just practically impossible for the sort of thing you want to do. So you can't have it in low Earth orbit. That's the first thing. You've got to be a long way away. And then you've got to shield it from the light of the sun, the Earth, and the moon, which is why I have this gigantic sun shield that is literally the size of a tennis court.
That's amazing. It is an amazing piece of engineering as well.
Yeah, there are something like 400 mechanisms have got to operate before this thing is ready. After it leaves the top of the launch vehicle, it's all folded up like a piece of origami. And I think there's, I'd have to check the numbers, but there's something like, I think, 280 motors or 380 motors. There's all sorts of latches and bits and pieces. So, the NASA, the Pathfinder guys talk about 7 minutes of terror landing on Mars, the lander that's coming up in February. 7 minutes of terror.
Yeah.
These guys are amateurs. We've got 11 days of terror on James Webb.
Yeah.
It's going to be an absolute nightmare.
It's got to get out to where is it? The Langrennen points. Is that how we pronounce it? The L1, L2. So it's L2. It's parking.
The second Lagrange
Yeah.
point.
Yeah. Well, Lagrange, isn't it? Yeah. So that's that's got to be way out, isn't it? Beyond Mars and
No.
that way.
It's about 1.5 million kilometers, about a million miles, if you want to do it in miles. So it's about four times the distance to the moon. So your way
doesn't sound too bad when you say that.
No, but it's going to take about 6 months to get there. Sorry, it takes about a month and a bit to get there. And then it takes a total about 6 months to get the whole thing set up, ready to observe.
Right. Yeah.
So, and it's actually going to go straight out, launch an Ariane 5. It'll go straight out. It won't go into orbit around the Earth. It just heads straight off. It'll go past the moon within, I think, a day. It took Apollo 3 days to get to the moon.
That's right. Yes.
It was motoring.
Just off it goes.
And they'll gradually open everything out, and then it takes about. The biggest thing is the mirror segments. There's 18 individual mirror segments. Each one can be moved 3 degrees of freedom, in, out, up, down, side to side. They can also rotate about each of these axes, and they also have little actuators on the back. You can actually alter the radius of curvature by a small amount.
Yeah.
10 degrees of freedom on each of the 18 mirror segments. Wow. And they've got to be motored into position and lined up perfectly. And I remember going to one talk at a NASA meeting where the guy explained the algorithm to tune up the mirrors. And the algorithm was mind-bending, the things they have to go through. So it's going to take a long time to tune those mirrors. But once they've got it sussed, it should be something absolutely incredible.
So I thought it was fun collimating a Schmidt-Cassegrain, but that's a different league. Sorry, Andy, over to you.
No, not at all. John, I mean, obviously everybody hopes and prays, and we've got all our fingers and legs and whatever else crossed that everything is going to go smoothly. If it doesn't, if the telescope fails to deploy correctly, if it undergoes, even a disaster of a launch, which God, let's hope not happens, but if there's a major problem with it and it just doesn't work, what do you think will be the impact on space astronomy for the future?
I think it's a massive loss. I mean, having worked in the business, I've worked, fortunately, none of the spacecraft I've worked on have ever been blown up. I mean, I've been out to Kourou and put satellites on top of rockets and watched them go, and I've been involved in orbit delivery of spacecraft. But I know people where they worked on 3 different missions. Each one was blown up by a different rocket on launch.
Oh, dear.
No rocket is totally reliable. I mean, Ariane 4 was one of the best workhorses, and that was something like 97.5% reliable.
Nice.
Which still means, 2 to 3 missions out of 100 are going to go bang. Fact of life. And I know, talking to a lot of the scientists and astronomers, they're terrified of the launch, and you just have to say that's the way it is. I mean, people are going to be doing everything they can. Ariane don't want this to go wrong. There's a lot riding on this, but what do we lose? We lose a huge amount. I mean, apart from the loss in money and time and so on. If you look at some of the instruments on there, the advance over anything previous is enormous. Now, there's an old rule of thumb that says every time you get an order of magnitude improvement in some capability, so that's like a factor of 10. So 10 times better resolution, 10 times faster processing of data, whatever it is, a factor of 10 has always produced radical discoveries, which are Nobel Prize time.
Yeah.
Now, some of the stuff on James Webb is not an order of magnitude better than anything before. It's 5 orders of magnitude better. It's 100,000 times. And there's nothing planned for space or on the ground that's like it.
No.
So that's what we say, the discovery potential is just enormous.
But what about the knock-on effect and the attitude towards funding future space astronomy? Because if you remember when the Hubble telescope launched and the mirror hadn't been ground correctly, the politicians were really out for the scalp of NASA in the States.
Yeah.
And there was a really vitriolic campaign against NASA. And what worries me with the James Webb is that, you know, future missions like the Roman telescope, which, you know, even up to now has had funding problems.
Well, burst and all sorts. Yeah, there's, I mean, the Hubble issue, we work with a lot of the guys at Goddard Space Flight Center, which is the, you know, where they're running the project from, just outside the Beltway at Washington, DC. A lot of the optics guys had worked on Hubble, and they were still scarred, and you could see it. You know, I could talk for hours. I better stop. But some of these guys would come up with the most incredible scenarios. So, like, you present, look, here's our test results. Look, everything is lined up. It's really brilliant. And they'd say, yeah, but maybe what you've got is you made an error there, and that was compensated for by an error here, which of course is what happened on the mirror grinding. You know. Yeah. And then this happened and that happened, and that's why you think you got a good result, but actually it's all wrong. Yeah. And we just have to say to these guys, you're off your rocker. You know, for all that to have happened, just exactly to compensate. You know, it's not credible. No. But you could see they'd been excoriated. You know, they looked haunted, some of these guys on the optics team. And that's why you got 7 degrees of freedom on the mirror segments, because you can't go, and even a shuttle had been flying, shuttle doesn't go higher than low Earth orbit. So the shuttle could never go and fix it. No.
So is this lessons learned from the problems from previous? The problems that we had with Hubble, you learn from those mistakes, don't you? From the problems that you have. So with the James Webb, have we learned from previous problems and you take that into account?
Learn from the challenge with most space things is you're trying to do something nobody's done before. You're pushing the boundaries a bit more at the time. So you're always doing something new, but at the same time, you're not allowed to fly anything in space. It's not being what we call qualified. So you've got to test it and show it's going to work, because you can't go and fix it. So that's why the electronics are always a bit out of date, because you've got to have been around long enough to have actually checked them out.
Well, that's my thoughts with all the missions. You think of the Apollos when the first Apollo 8 went to the moon, then 10 was the trial before it actually touched down on the moon. 11 lands on the moon, but the technology is from the late 60s or probably the early 60s to get them there for the 70s. And then when you get the Voyager and the Pioneers going out there, you're using technology from, again, the 60s, the 70s, and it's still out there flying. It's still working. I say flying. I use the wrong word. Flying is wrong. But,
you know, that's what we call it. The thing that gets launched is called the flight model.
Yeah.
You build all sorts of test models, development models, structure models, thermal models, electrical models, and the flight model is the one you fly. And but I can tell you, going way back into the 1980s, I worked with what at that time was a Canadian company called SPAR. Nothing to do with grocers. And it was
well, the grocers are available.
Yeah, it was the Remote Manipulator Systems Division at Downsview, Toronto, and they built the shuttle arm. These are the Canada arm.
And
the guys we were working with, some of the guys I was working with, had been there, and I used to go out there fairly regularly. And I was actually taken into the actual simulator where they train the astronauts. They got an arm on a big room on air pads, so it's kind of frictionless. And then you actually had a mock-up of the back of the shuttle cabin with the controllers for the arm and the windows. And this represented this is where the astronauts came in there to train. And I remember going in to look at it, and it looked like something out of a 1950s TV set. It was primitive. It was sort of, I have to say, it's the sort of thing you see at the RAF Museum at Cosford.
At Cosford,
The controls were all sort of clunky, and it was like, this is the space shuttle. Wow. It really did look dated. And that was even then.
I mean, the flight deck of the shuttle, when you look at photos of the flight deck, it's absolutely amazing. Like every single dial, knob and switch in the world was requisitioned to put on the flight deck of the shuttle. It's true. And you look at the flight deck of the SpaceX's Dragon, and they're just sitting there with 3 LCDs
Yeah,
the
exactly.
flat screen.
Yeah.
You know, it's amazing the difference.
Yeah,
is
but that's the way you think. You know, as you say, when you build something, you're designing it with the technology that existed
That
some
you've
years
got there.
ago.
Yeah.
With all these delays, you know, these things. We're seriously worried about the various instruments because most of them have some sort of mechanisms inside. You know, things have got to, wheels got to turn and bits have got to be moved. And you know, mechanisms are the things that always go wrong in space. They wear. And we've been testing these things on the ground for umpteen years. You know, it's not far off its wear out date. We haven't launched it yet. So yeah, there are big concerns about the time it's been delayed. And I have to say, a lot of people are very seriously rattled about these, what went on at the prime contractor in Los Angeles. You know, it really rocks people's confidence with some of the things that happened. The sad thing is that all the instruments were put together, and you know, NASA love acronyms. So the instrument suite's called ISIN. By the way, Pete, am I all right rambling on like this? Or
No, you're fine. You carry on.
It is fascinating. I'm a medical engineer, so I work with medical equipment, not as the equipment that you're using, but the principles of engineering is all the same, isn't it?
Yeah.
I'm thinking of in the Mercury and the Gemini and the Apollo. You know, they're using analog systems, analog needles, analog dials. Anything that looked digital was a little like a roll, click, 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 and then all of a sudden that's gone, and we have these LEDs or red LEDs and the green ones, and the technology changes, so there's less moving parts, but you've got more electrical connections. You got microchips, which, you know, a bit of static, it doesn't go down well. Any fluid floating around in the capsule can be a potential. So you go from one technology to a better technology maybe, but you still got problems.
Well, you see, one of the original things, when you go in a spacecraft clean room, you know, you can't take a pencil in, because if a bit of pencil lead goes off, that's a bit of graphite.
The graphite, yeah. Conductive? Is graphite conductive?
Yes, it is.
It is, yeah. I'll get my meter out tomorrow and test that.
I'm going to say,
you have a fun life, Dave.
I do. It's COVID.
The instrument pack was known as ISIN, the Integrated Science Instrument Module. And that was the NASA terminology. You know, there was an ISIN team. So MIRI was a collaboration between Jet Propulsion Lab and these 32 European institutes, 10 European countries, all run from the UK. One of the other instruments comes from ESA, with quite a few NASA bits in it. There's a Canadian, it's the Fine Guidance System that's also got, it also doubles as an instrument. And then there's the American instrument, and they've all got wonderful imaginative names. I remember when it first got involved, it said, why is it called MIRI? Because it's the mid-infrared instrument. So, well, that's not very imaginative. Why don't you call it Fred or Olive? Or, you know? and the American instrument is called NIRCam, the near-infrared camera.
Yeah.
The European one is NIR-SPEC, the near-infrared spectrometer. And the Canadian one is the Fine Guidance System, FGS. But these four instruments all get put together in this big carbon fiber frame. Now, MIRI, to give you some idea, it's about roughly a cubic meter, and the thing is about 100 kilograms in round numbers. I have to convert things if you want to work in imperial units.
Sorry.
But anyway, I mean, you think of a box, a kind of a meter cube, that's roughly MIRI.
Yeah.
So you've got these four instruments in this big frame, and that goes through a whole load of testing down at cryogenic temperatures, because you've got to test it cold.
Mm-hmm.
So it's you've got to cool this thing down in a giant chamber to liquid nitrogen temperatures, which is minus 180 C. And it takes a long time to cool all that support metal work and all the stuff down. Mm. And if anybody's not connected a bit of instrumentation or a thermocouple or something, you know, properly, you've got to recover it all.
You're going to find out, yeah.
So the testing is, it's months of testing. Mm. But when they start testing, it's round the clock, you know, 24/7. All the engineers are on shifts and the scientists and so on. But there's a massive amount of testing to do. And then having got all the instrument tested, you've got to vibrate it and you shout at it, called acoustic noise testing. And then the whole thing was shipped down. At the same time that's going on, the actual telescope, the main 6.5 meter diameter mirror and its sub-reflector and all the bits are put together. And then the instrument pack, ISIM, goes on the back of the telescope because it's the light comes off the main mirror up to the sub-reflector and then back through the hole in the middle of the main mirror to where all the instruments are that pick off the light. So the telescope is known as the OTE, or optical telescope. Optical telescope equipment. I've forgotten it now.
It's okay.
Anyway, you put the OTE together, the ISIM, and they called it Otis, which is either an elevator or something to do with Otis Redding, and that's the
Otis Redding, yeah.
Instrument pack. And the Otis was then shipped down to Houston in Texas at the giant chamber where they actually did the Apollo, the moon landing chamber.
Yeah.
Vast thermal chamber, colossal. And what they actually did was they suspended the telescope with the instruments on the back on big bungee cords with an artificial sort of universe projector above it to actually shine light down, and they could check things out. And they had to pump this enormous chamber down to vacuum, cool the whole thing down to -180. In fact, they weren't even colder than that in some places, and then test it. And that took many, many months of testing. Now, all that was going on, in theory, while this was happening, the prime contractor was putting the spacecraft bus together in Los Angeles, and then they get put together and go through the final testing and off to the launch site. Now, what happened was, the really sad thing is, the telescope and the instruments all checked out beautifully. Everything was fantastic. It got delivered to Los Angeles and it sat in a box for months, waiting for them to sort out the basic problems on what should have been the simplest bit, which is tragic, really.
Amazing.
But that's where it is. Anyway, they finally got it all together. They've only recently done the final big deployment test. So what they do here is you have to test it as it will be in the launch configuration, because you can't test it. You can't put the whole thing into a big chamber to try and test it in the space condition. It's just too big. So what they do is the whole thing is folded up, and if you go on the NASA website, you can pull out some wonderful animations of how it all unfolds and so on. But in the launch configuration, it's then checked out. Well, in fact, having put it all together, you then deploy the sun shield and open up the telescope and so on. And that's where they hit one set of problems. That slowed everything down. And basically, this was, where were we? I think that was 2018. I'm losing track of time. And that was like the second major wobble where they were really worried. It was obvious they weren't going to make the launch date they were heading for. I think that was the 2018 date. And that's when they had to move it back yet again. But before that, around about 2011, 2012, the project nearly got cancelled completely because of overruns at NASA. And we were all working to ludicrous deadlines. And we could see this was all going wrong. And I remember a lot of the Europeans saying to the Americans, look, you guys are in real trouble. There's no way this is all going to come together in the time. You ought to be doing something about this. And no, we're too big to cancel. They literally thought that NASA, we are the prime project. It's the only NASA Nobel laureate is the chief scientist on James Webb. And he's a lovely guy, John Mather. And he, NASA saying, look, we've got the Nobel laureate working on this job. We're the prestige job. We're the number one. Too big to be cancelled. And of course, they nearly were. I can remember the shot with some of the guys at NASA saying, bloody hell, Congress are out for it, And of course, they were looking for another $4 billion. It's not, it's like...
it's difficult getting the money in the first place and keeping the project going.
It's not exactly pocket money, is it?
Not really, no.
Quite a few people in Europe, we were actually having our own private discussions. Look, the way this is going, they're going to can it. This is way over budget and over schedule. What can we do with the bits we've built in Europe? You know, are there things we could do to sort of use this stuff somehow? Because we can just see NASA being cancelled.
Yeah.
And when the penny finally dropped, it was a real blow. I mean, they were saying, the guys on the project at NASA thought they were untouchable. And then it was a major, I could go on for hours about this. Some of the things that happened were just unbelievable.
What we'll do, we'll go to a record. I've said that again. I
Record, a vinyl.
Go
Not even a track.
and then we'll come back. Before we go over to the track, I've got a message in from Stefan from Russia. He's still tuned in. And he said, this is beyond interesting. It's amazing.
Thanks, Stefan.
Yeah.
Well, this is what we want. Yeah.
Yeah.
Fascinating. And I've got a message from Jill in Dublin. And she said, absolutely brilliant, John. Really enjoy listening. And she just said, I hope I haven't offended Dave telling him he was.
No, you never offend me. I remember the days of Jules Verne. I love these SpaceX rockets going off because it just takes me way back to when I used to watch them when I was a little lad.
Yeah, me too, Dave.
Yeah.
I'm with you.
Yeah.
And Simon was there painting the spaceship with Catherite. If you remember the anti-gravity
Yeah,
paint.
Catherite, yes.
Great
Up
stuff.
and down. Yeah.
Yeah. And then Tien in Japan said, this is fascinating, really enjoying it. So we'll go over to a track, and I was looking for something about something being in the sky, and what other track can we play? And I thought Lucy in the Sky with Diamond would be
Brilliant.
It's good.
John,
okay, folks. How you doing?
Yeah, okay.
Fine,
Not
thank
bad.
you very much. Thank you.
I ought to say, it might sound like I'm kind of knocking NASA a lot. Don't get me wrong. I've got enormous respect. They've got some absolutely brilliant people.
Yeah, and you've been knocking Issa during the break as well. So you've been doing it to everyone.
It's a fine balance.
Saudi Arabia, the Russians, everything.
No, I mean, the thing is, the Americans do have a way of doing things, brute force, if you like, where they will throw money and people. And in Europe, we just don't have the number of people and the amount of money to do it. So the Europeans tend to be much more, if you like, systems oriented in terms of working out the best way to spend the resources they've got. We just don't have that luxury the Americans can have at times. Again, I could talk about some of those.
That is rather the American way, though, isn't it? It always has been.
I've seen it in all sorts of things. But I mean, just going back to where we were, I'm going to say that in terms of James Webb, what happened was we finally got the whole thing put together, checked it out, having sorted out the problems when they first deployed the sun shield, put it all back together. It's been put through some thermal testing, some vibration testing, some acoustic testing, and then check things out. And then in the last few weeks, they've actually done the final major deployment, the last full deployment of the sun shield. Now, what you're trying to do is say you're trying to get this thing that's thin layers of Kapton, it's like aluminized foil. It's people compare it with baking foil, but it's not quite the same as that, but it's that kind of thickness. And there's 5 separate layers, and they've got to be spaced out. And it's the size of a sun shield. And when it opens out, it's opening out in effectively 0G. But you're testing it on the ground with gravity. So, knowing you're testing it in the right way in itself is a major challenge. I mean, the sun shield, it's a massive development exercise.
John, I was just thinking of the material in astronomy. As amateur astronomers, we use film, solar film, Barda and Mylar.
Yeah, it's kind of like that.
Yeah. So is it that thickness? Is it but layered?
It's very, very thin stuff. But the thing is, it's all going to be tensioned. And the 5 layers, the way the geometry stacks, it's also very specific. And the way it works is the spacecraft bus, the control box, if you like, is on the sun side. So when this thing is in, we say it's gone out to L2, but actually it's in this giant halo orbit. It's sort of doing a circle, if you like, along a radius from the sun and the Earth out to L2. If you imagine a circle going around that radial arm, and on a vast scale. I mean, L2, you say it's a point in space, it's a vast volume of space. And it's just, it's got this property that you don't need to burn a lot of fuel to keep the spacecraft there. So it tracks around the sun at the same speed as the Earth. Now, you all know, obviously, the further things are out from the thing they're orbiting, the slower they move to be stable. So it ought to be sort of dropping behind the Earth, but that will give you all sorts of communication issues. But at L2, owing to some weird mathematics, when you work it all out, you can keep a spacecraft there with very little fuel burn to keep it in that position.
John,
you've got to keep it with the sun shield between the telescope and the instruments and the sun, the Earth, and the moon.
Yeah. Michael? Yeah.
Yeah, John. One of the things I've always been fascinated by the Hubble deep field and the ultra deep field images that they did a few years ago.
Yeah.
What would the James Webb be producing anything similar to that, or is it different?
Oh yeah, yeah. No, they. I mean, the hope early on was they would be able to operate the two together and actually do the same things and help cross-calibrate.
Right.
Now, then Hubble started having all these problems. James Webb was delayed, and people thought it would never happen. But it may be Hubble can hang on, by the skin of its teeth.
Right.
I think one of the very first targets. It'll depend when it's launched.
Yeah.
What you can look at, because you've got to bear in mind, it can look at if you like, at a swath of sky. You can't look across towards the sun because that would, kill it.
Yeah.
But over a year, it will be able to see the entire sky. But you can't just point at anything at any one time.
Okay.
You've got to keep the sun shield between the Earth, the Moon, and the Sun.
But it will be doing planetary science as well, won't it?
Oh yeah. Look at the planetary. One of the early ones that I know, going back quite some time, the astronomers are very keen to look at Vega as one of the early things, because obviously it's got a protoplanetary disk.
Yeah.
And one of the great things on the mid-infrared instrument, we've got 4 coronagraphs where we can, the 3 of them are like the physical bit. There's an actual bit that blocks out the star, so you can point this thing at a star, and then when you look at this thing, and they're tuned to specific wavelengths of light, you can actually hopefully blot out the star with it's a LIO, LYOT coronagraph. There's a physical bit that blocks out the star.
Yeah.
And you might be able to get the light from a planet or planets and analyze that. There's 3 others that are actually what we call 4-quadrant phase masks, which are very clever little optical devices that effectively null out the host star. So you direct the light onto these things, and they're tuned for 3 different frequencies, 3 different wavelengths, if you like. And so you can null out the star in the center of this 4-quadrant phase mask, and then collect the light from a planet, and then that light goes through the spectrometers on MIRI. Now, I'd put a word in here because the optical design was done at the Royal Observatory, Edinburgh, and the spectrometers, and there's a long wave and a short wave spectrometer. These things are just works of art. There is something like 900 optical surfaces in these things. Most of the optical surfaces are polished aluminium. MIRI is basically all aluminium, because we know how aluminium contracts. Now, bearing in mind, this is going to be designed and machined at room temperature, but operate at minus 233 C, or 40 degrees Kelvin. Okay, so this is the triumph of mathematical modelling, and real engineering. You actually, equations you learn at school about, coefficients of expansion, aluminium, I can still remember, it's about 24 times 10 to the minus 6. It actually means something. You machine this stuff at room temperature. You put 900 optical surfaces together, including wheels and filters and dichroics, all sorts of things. And you cool it down in a test chamber, these cryogenic temperatures. You shine some light in. And I remember the first time we did it, we tested at the Rutherford Appleton labs in Oxfordshire, in a big cryo chamber. And the detectors, the pictures came up, and the images were bang square in the middle of the screen. You know, the image is lined up beautifully, and that is just a triumph of
Wow, that's amazing.
calculated engineering.
That must be a good buzz. People involved in the background and the design, and then you press the buttons, and it's
there's the shot. Wow.
Which brings me to another question. You know, for you, assuming James Webb all works out and it makes these amazing discoveries, which we presume it's going to,
it
for
will
you,
work out.
you will have been involved in history. You know,
that's the thing. That's why I want to survive COVID. I want to be there.
That's a good reason.
I want to be there when the Nobel Prizes go on. And I mean, on a sadder note, the lead scientist, and I could pay enormous tribute to Professor Gillian Wright. She led the NIRI consortium. She is an absolutely amazing person, very good scientist in her own right, but politically savvy as well. I mean, it's a rare combination of, you get a scientist, astronomer, it's like getting same with an engineers, you know, getting those to actually know how to manipulate the finance people and the system.
We need more like them.
The politics.
Yeah,
if you want to see people being nasty, you want to see professional scientists. They can make politicians look like kindergarten. You know? they can be so nasty to each other, but equally, they know how to collaborate. And Gillian, just amazing. She devoted a huge chunk of her career. And the thing is, she's going to retire soon after it launches, probably.
Yeah.
And she was doing this, you know, because as the lead, what they call the principal investigator for the European side of NIRI, she gets dedicated observing time to herself.
Wow.
And she had got sort of plans. And as she said, you know, I'm no longer doing this for me. I'm doing it for the next generation of astronomers. But these, you know, almost certainly there are going to be discoveries made that result in Nobel Prizes.
Yeah.
Oh, yeah.
Well, are we going to be able to peer inside the core of a galaxy? Because you have this, you know, lots of stars in the center and lots of gas. With infrared, you could actually look through all that, couldn't you?
Yeah, but you've got to remember, because it's along a wavelength, you won't quite get the same resolution. Yeah. But the thing is, because it's such a big mirror, you get that much more light coming in. You're going to see a hell of a lot. But to give you some idea, I'm doing this from memory. So I think the resolution at 1 micron wavelength. So for those not sure, visible light is roughly 0.4 to 0.7 microns wavelength, and then the near infrared is, in broad terms, 1 to 5 microns, and the mid infrared is 5 to, I don't know, 30 or 40 microns, and then you've got the far infrared beyond that. These are the wavelengths I'm talking about.
Yeah.
A micron, I think, at 1 micron, James Webb, the telescope, would be able to detect a 1 penny coin, I think, at 40 kilometers. I might have got that wrong. I'll have to go. It's some sort of ludicrous. You know, what it can see is just amazing.
Talking of stuff,
I was just laughing to myself there. Sorry, John, I was just laughing to myself when you said a penny. A lot of the textbooks that we read over the decades, it's always a dime held at 3 miles away, and the telescope could actually see that resolution. But this is the Imperial penny, of course.
The Event Horizon Telescope, which took the famous image of the black hole in M87. That resolution was capable of seeing a coin in New York from London and being able to read the writing on the coin. That was the, you know, that is just.
You've got to be very. You've got to about what wavelength you're talking about to make it a.
Sorry, Michael.
Sorry. Talking about things closer to home. What about planets in our solar system? I'm
pretty sure they're going to be able to certainly look at Jupiter and Saturn and you know the.
Yeah, that's what I was thinking. Yeah.
What you've got to be careful of is obviously putting too much light into.
Of course,
you know, the control of this thing is going to be very, very careful. We don't want to go and destroy it at day one. But I mean, while I was still working on it, so we're going back, 2012, they'd actually released the the draft observing templates to the astronomy community for comment, sort of thing, about, because it's going to be run from the Space Telescope Science Institute at Baltimore.
Yeah.
10 people with STSCI operating Hubble are going to go and operate James
Well,
Webb.
they're going to have a follow-on, aren't they?
Well, yeah, but I mean, it's that continuity and that, ability to compare things. But yeah, just talking about that. So what happens is the observing time is divided up. So Europe, by definition, the deal was at the beginning, we get 15% of the observing time. I think Canada gets 5%. NASA, I think, gets the rest. And then it's subdivided again into, so the principal investigators, the lead scientists, get their own personal allocation. And then each European of the 10 European countries on MIRI has their own lead investigator who will get some observing time for themselves. Now, how they divide these things up, or what they want to look at, some will collaborate and share, and people have their own different things they want to go and look at. But for instance, so Gillian's got some of her own time. Just going back to the Hubble Deep Field, I think that was the director of STSCI.
Right.
I think he had a certain amount of his time, and he decided to do the Hubble Deep Field.
All right.
And I think that's how that came about. But he said, let's just stare at a bit of space that looks empty.
Yeah. And look what happened.
And look what happened.
But that's dark adaptation for you, isn't it? The longer you stare into the sky, the more you're going to see.
But, hey,
And talking about collaboration,
and in any direction you can do that.
With different countries, when you speak to people generally about space missions, lots of people immediately think about NASA. Now, the James Webb isn't just NASA; it's like a worldwide, collaboration.
Yeah.
How do we, tell people what the sort of percentage it is, for instance, of the Europeans and the British, and I know lots of the design work has been done in the UK. How do we get that across?
That was one of the problems. And I mean, to be blunt, ESA aren't very good at publicity. NASA's got it off to a fine art. And of course, everything is NASA. And it always brasses me off no end when some of the radio and TV presenters, if there's anything happens, they've got to go and say what JPL did or what NASA did, Because, hey, if you've got a choice of going to Pasadena or top of a mountain in Europe, it's a bit of a tricky choice, isn't it? But Europe pioneered infrared astronomy in space.
Yeah, absolutely.
You get that. And
but isn't part of the thing with NASA is that it's taxpayers' money. So the US taxpayer pays for all that NASA projects. So they've got to justify anything that goes on. They have to justify the cost.
But I mean, I know because I worked in a pan-European company for 30 years and been all around Europe, different sites and so on. And the thing that always got me was, if you were in, say, France or Germany and an Ariane rocket got launched, it was on the news. It was headline news. It was on the television. Another European space triumph. In Britain, the attitude was, and I know because I knew the PR guy at Stevenage very well, and I remember him saying, we try and get people to go along to see a look. Look, it's a British-made spacecraft. It's going out from French Guiana. Oh, no, we're not interested. Give us a call if it blows up.
We don't
want to shout about things that are good. That's just the British.
But it used to be different, though. I mean, if you think back to what's a good example? Giotto at Halley. When that was broadcast live on the BBC, the encounter, and you just wouldn't get that these days at all.
No, it's a shame. But if I give you sort of British involvement in MIRI, for instance. So I worked at which is now called Airbus Space and Defence at Stevenage, and there was only never more than 6 of us as the core team. But we coordinated the entire European collaboration. So we provided the system engineering to bring it all together, and the product assurance, which is a really important bit of the whole picture, and project management. Now, you've got up at the Royal Observatory, you've got the principal investigator, Professor Wright. and she got the optics engineers and some of the key astronomers there, and they made some of the bits of the spectrometer, which is incredibly complex. Some of those bits were made at Cranfield, other little European, UK companies. Cardiff University was involved. Leicester University had a major role on the structural design, and the MIRI, because MIRI has to be colder than the other instruments because it's in the mid-infrared, so it's more sensitive to temperature. So MIRI actually runs at about 6 degrees Kelvin, 6 degrees above absolute zero, whereas the other instruments run about 40 Kelvin. Now, James Webb will naturally cool down in space with the cold side, because deep space is 3 degrees Kelvin in round numbers, okay? And if you keep looking at deep space, it will naturally cool down. But you've got heat flow coming in because the telescope has to be attached to the bus on the hot side. So there's heat flow through, there's got to be. So, but then you can achieve a balance with some very clever engineering, a lot of which was done by the NASA guys, of course. You can get the telescope to run at about 40 Kelvin, minus 233 C. But MIRI needs to be colder because it's in a longer wavelength. So we actually have a cryo cooler. Actually, so it's like it's a fridge, put it in simple terms, which actually the main bit of it is in the spacecraft bus side, the hot side. There are then helium coolant lines that run through from that up through the tube that supports the telescope and instruments. And then the cold head is at 6 Kelvin on MIRI. In fact, there's a number of cold heads, and it's a fairly complicated system. But I mean, in simple terms, we have this chiller for MIRI, and it's inside a thermal box of its own inside the ISIN, the instrument module. And so, you know, we've got to be really cold. Now, MIRI is then supported, it's all aluminium, but it's supported on a carbon fiber hexapod to thermally isolate it from the rest of ISIN. And that hexapod was designed in Leicester University. The mechanical analysis was done by Leicester University. Bits of it were built by the struts were built by the Danes, for instance, and bits were machined at various places in the UK. You've then got the Rutherford Appleton labs, who did some of the science. That's where all the testing was done. The whole thing was brought together at Rutherford Appleton. And there's a whole raft of people in the UK being involved in this. And of course, we're all going to be waiting with bated breath. It's not so much the launch, it's more the deployments, you know, the 11 days of sheer terror. And I think it's like 200 single point failures on James Webb.
My goodness me.
Which, you know, single point failures are inevitable on a spacecraft, because somewhere, you know, if you want to say release something that's been stowed for launch, you've got to break, you normally have a pyrotechnic nut or a bolt, right? You can't have a redundant one because you've got to break that one as well. You know, there are inevitably single point failures. Everybody gets twitchy about them, but we've got an awful lot, mainly to do with deploying the sun shield and so on. So people are going to be twitching like mad when all that goes on.
Yeah, it's going to be twitching all the way, isn't it? I mean, it's not just getting it on the launch pad, getting the thing into orbit, getting it out of orbit, getting it out to L2, and then when you get there, you've got to uncurl this huge shield.
It starts unfolding shortly after launch.
Really?
It comes okay. Doesn't go into orbit, it goes straight out towards the moon. Well, yeah, the moon's orbit.
Yeah.
Whizzes past the moon in no time.
And
but the first few hours, first thing you're going to do is deploy the solar array to get some power to it, because it's been running on for some time. You've got to get the telecommunications antennas out, the high gain antenna and that sort of thing. And then as it's creeping out to L2, that's where you start deploying the sun shield, opening that out, folding out the sub-reflector, folding out the two wings of the main mirror. You know, all these things are going on, and you actually start tuning things up on the way out there. And then you get out to L2, and there's this long process.
Right. So by the time you get there, hopefully, but I can imagine everyone who's been part of the progress you're going to have your launch team, you're going to
Yeah.
have your deployment team, and then the experimental packages, and then will it cool down enough? And
yeah, if any of our listeners wants to actually see this, Northrop Grumman, the prime contractor, have produced a 12-minute animation showing exactly how the spacecraft will deploy, how the telescope will deploy. You can find that easily if you just Google James Webb deployment video. You'll find it.
It's on the NASA website. Yeah, there are several. In fact, I've done an awful lot of talks on this. I'm still booked to do various talks, and I've actually got a video from early on that they've now withdrawn, which actually I think is one of the best ones. It's only like a 2.5 minute one, but it's one of the best ones for.
I've got that one.
People, yeah.
Yeah, it's brilliant. It's absolutely brilliant. Yeah.
Yes, John. I was going to ask you earlier, but you really answered the question. Is that with all the delays? I mean, technology hasn't stood still. Would you have liked to have upgraded some of the systems? But as you said, it's all been tested and everything now. So,
you see, we shipped Miri out. I think it was the 28th of May, 2012. We were the last instrument to start because NASA originally wanted it just to be a near-infrared instrument. And a lot of astronomers said, that's no good. You need a mid-infrared instrument because some of the things you're going to look at, you won't be able, for instance, you won't be able to tell the difference between a very old galaxy or an active galactic nucleus because their spectrum doesn't differ until you get out to longer wavelengths. So you've got to have a mid-infrared instrument to help differentiate things. Plus, it'll do things in its own right. Now, interestingly, Miri started out as a bolt-on addition because a bunch of European and American astronomers got together. This was Professor Julian Wright and George Reiki, one of the big names in infrared astronomy in the States. They were the two key players, and they put together a team to offer a mid-infrared instrument. Now, this was seen as a bolt-on that a lot of people didn't really want. In fact, it is now the only one of the instruments that actually is fundamental to all 4 science themes. And I mean, they all think it's the greatest thing since sliced bread. It's got the most complicated organization. To say you've got the Jet Propulsion Lab, plus, I mean, and some of the bits also come from Goddard. And then we've got these 32 European science institutes in 10 different countries, all funded independently from ESA. And this entire organization was put together. And we were the last one to start. We were the first one to deliver the flight instrument.
Wow.
Can I take
That was all down to the project manager, of course.
Yeah, the reason I asked is basically with the development of technology and all that, I was a bit concerned that basically it'd be like putting Pizza Nokia up in space as a communication satellite.
Some of these, some of the advances are that there's still nothing around or planned to replace it. So losing it, going back to what you're saying, and losing it, if it doesn't work, then so many things might not make it work.
And what do you think the knock-on effect in terms of space science might be? I mean, I can't see NASA getting that amount of funding again for such a complicated project.
No. When we had the 2014 debacle and this $4 billion increase, I mean, it was like 50% increase in the cost, sort of overnight. I think a lot of people were very worried. A lot of the other scientists, astronomers, were very concerned that James Webb was going to stop other projects going ahead, and perfectly reasonably so. But I mean, towards the end, a lot of us were saying this is probably the last of the great observatories, because putting all your eggs in one basket with all that development all on one mission. And if anything goes wrong, as you say, it's a huge loss everywhere. But also, we're not going to have that kind of money again.
It's the same as the Cassini probe, isn't it? That's the last of the big planetary probes.
Yeah, absolutely.
I think it's going to be some time before there's anything of this scale.
Can I just take you back to what you said? I think. Sorry.
No, go on, Michael. Go on.
Okay. You said something about the James putting it into storage for a while. Is that right? It was in storage.
Well, effectively, the telescope and instruments were waiting for the.
Yeah, I mean ready. I mean, The reason I say this, it reminded me of another famous probe, the Galileo probe that was put into storage after the Challenger accident.
Yeah.
And
look
of
what
course, and look what's happened with the antenna.
Yeah.
So
No,
hopefully,
there's a lot of people very seriously concerned about the length of time everything's been around.
mhm.
So I think I was saying, we shipped Miri out, the flight model Miri, we shipped out in 2012. It was nearly a year before NASA were ready to integrate the ISIM structure, the big space frame, if you like, all the instruments. And so, I delayed my retirement until I'd seen NASA put the thing in there, fully handed over. And then the other instruments came along. I mean, everybody has problems. When you're not knocking out Coca-Cola cans, you're doing something nobody's done before. And if you've been in this business, you know what it's like. Things happen.
Yeah.
Who was the famous? Was it Dick Cheney? The known unknowns and the unknown unknowns, all this sort of stuff. Well, you really are in the unknown unknowns in some of these things. And so there were various issues. Some instruments, various bits had to be changed at a later stage. But anyway, they got all this stuff together. And the sad thing is, it was what should have been the most straightforward bit, slowed it down. And then there were a series of really very distressing issues that delayed it even further. So we think now they've done the final big deployment of the sun shield, and it all looks okay. They'll be stowing that, and then there's all sorts of checkouts to be done. But hopefully, some point later this year, it'll get in this barge, be shipped down to Kourou, and then there's something like a nominally 2-month program at Kourou to basically do final checkouts there, put it on Ariane, and press the big blue button, as it were.
And another catchphrase that springs to mind is this is why we test and test.
Yeah. But one of the problems when you got something this big is there's another NASA mantra used to be test as you fly as you test. But when you've got something like the size of a sun shield, you cannot test it in a zero gravity environment.
No.
You can offload, you can try and do things, but you'll never make it absolutely the same. It's just impossible. So there are always compromises.
Bearing in mind that infrared astronomy really is the thing of the future. That, as you say, the only, if you want to go back to closer to the Big Bang, it has to be infrared. So you've got something out at the Lagrange point where it can't be maintained, it can't be fixed if it goes wrong. In the future, I mean, I don't know how far in the future we're talking. I presume that, putting observatories on the far side of the moon would be, one way to do more infrared. I don't know whether it would get the same value as the James Webb Space Telescope, but at least it could be maintained and repaired. So I don't, this is something that astronomers have talked about for decades, putting something on the far side of the moon.
Well, I think originally it was radio telescopes.
Yes, that's right.
Brilliant location, but yeah, I mean, the other thing is if things like SpaceX's Starship does actually get performing, potentially you could see that being used for something like L2.
Absolutely.
We're a long way in the future on that.
Yeah.
But you see, I think the original requirement on James Webb was it was supposed to be designed for a 5-year life, but with the aim of it lasting 10 years. Now, the thing about space hardware is generally, if you get over the infant mortality period, because a lot of things do fail quite early on, but if you don't have early failures, they nearly always exceed their design expectation.
Yeah.
But isn't it cryogen limited then?
No, you don't need any cryogen. You see, because
not for Miri. Okay.
No, it's a cryo cooler. It's actually not kind of cryogen. It's a heat pump, if you like.
Wasn't Hubble's design like 15 years?
Sorry?
Wasn't Hubble's design like 15 years, wasn't it?
Oh, I can't remember. But I mean, the feeling is it will cryo coolers do fail because you've got moving bits in very cold temperatures. It probably is going to be the cooler, but you know, spacecraft get hit by micrometeoroids. They get degradation, oxidation. You've got UV, all sorts of radiation coming in. So things degrade, and generally most spacecraft are limited by the power output from the solar array at the end of life, because that degrades all the way through life as it's, you know, hit by various things and so on. So generally you tend to run out of power or station keeping fuel, but you just don't know. I mean, the first thing is to get it out there. I kind of thinking if it all works, it'll keep working for quite a long time.
I mean, look at Spirit and Opportunity on Mars. I mean, they had a design life of 90 days and they just kept going and going for years. They were amazing engineering, absolutely amazing engineering.
Well, I remember some of the spacecraft that built at Stevenage back in the early 80s, their design life was something like 5 years. And some of those would be still going 20 years later.
Yeah.
Well, I've said this before, I think, and you know, space missions in general, they're so long in their life. They provide employment for generations. You know, with not only the building of them in the, to start with, but actually trawling through the data later on, for instance.
Yeah.
Okay, panel, we're going to go over to a track, Deep Purple and Space Truckin'. So we can't hear it in the studio, so we will have to listen to the play when it goes out.
It's
which telescope, refractor or a reflector? What would you prefer? As amateur astronomers, what would we go for? Depends what you want to observe, I guess, doesn't it? Are you into deep sky or are you into planetary? What if you're into a bit of both? A bit of a mix.
I've got both really here. But not that I use telescopes very much here, as you know. But I've got a 4-inch refractor, triplet, Explore Scientific, and a 10-inch Dob. So it's horses for courses, isn't it? You know, with my solar and my lunar and my planetary, I would use my refractor, and for my deep sky, my reflector. That's
so the refractor, you'd have what, an aperture of 4-inch or 3-inch or thereabouts?
Well, the one I got's 4-inch.
That's 75 millimeters to 100 millimeter, isn't it? In metric.
102 millimeters.
Oh, 102.
Look, I can do maths. Not really. I failed it at school, grade 4 CSE.
That was always the advantage of the abacus. Never had a problem with it.
Well, they did have abacuses in my day, and just before my mobile phone, actually.
We actually had them in my school as well, in the juniors. But,
so I would say, yeah, from my perspective, I love using my refractor because it's carbon fiber, it's light, it's easy to put outside, it's great quality. I like looking at the moon, and I like imaging the moon because it's easy, and that's the other reason. So I would prefer my refractor, but you know, some nights I do go out and star hop with a Dob. So I mean, Simon, what would you prefer?
I'd go for a Dob. It's the desert island question. So I'm going to have an 8-inch Dob float along.
You'll have to explain what a Dob is, because some of our listeners may not know. It's a
reflecting telescope, Newtonian in style, but it has a really simple mount. And one of the reasons for that is I do lots of outreach, and I used to do lots of outreach up until March 2020.
We'll do it again.
If I put a classroom of kids with a tripod and a mount where you've got to twiddle knobs and do all that, they get confused, they get bored, whatever. If I put a Dob in front of them, they just drag it around, point it at what they want, they just look up the tube, really simple, and they get great images. They can see how it works as well. They can actually stare inside and see the mirrors. And so it's really sort of an easy piece of physics to teach.
It doesn't have to be a technical telescope, does it? No. It's a mechanical functioning telescope, altitude and azimuth. Lift it up, lift it down, or move it down, rotate it at 360 degrees. Yeah.
You're going to think
quite simple.
Is this when I was a kid, and when I first had my Dob when I was a kid, when I was 30 actually, so that's a long time ago. I used to get a buzz looking down the tube at the mirrors and stuff. I don't know, am I just weird or something?
No.
I think we all do that.
You have to look down the tube.
Got to check that mirror.
the amount of times I've done sessions where you're looking through and suddenly the star or the moon disappears, and this is a kid looking down at the mirror, and everyone just drawn to looking straight down. It's lovely.
I have got to say, on some outreach events, we've had a young teenager, let's say, who thought maybe it's a dustbin. I could throw my piece of paper in there, which they found amusing, but it wasn't so amusing when you've got to get that out, and hopefully it hasn't scratched. It could equally have been a can of juice, couldn't it?
It could have been.
But these things do happen at outreach events. But yeah, Dobsonian is great telescopes, and they come in various sizes. Tend to be about 6-inch aperture, 150 mil upwards. I'm saying 8-inch. That's what. Come on, help me out. It's 100 mil.
Yeah.
Yep, 200 mil metric. A good aperture. So the advantage of a large mirror brings in lots more light, which means you see fainter objects. You've also got better resolution, but you do have the downside that your secondary mirror could be in the way, and you may lose a certain percentage of the light going in.
Yeah,
and therefore reducing contrast as well.
Just got a question.
But it's not a big problem, is it?
Got a question from Rod in Los Angeles. And he wants to ask Simon, okay, you're going to a desert island. Why are you only taking an 8-inch dob? Why aren't you taking as big a dob as you can get?
It's a good point. It's a good point.
Brexit, that's why.
Damien Peach told me last night there's no point ever getting anything bigger than a 16-inch because you're never going to have the seeing conditions that are actually going to get the best out of anything bigger than that. So actually, I've got a back. And if you've tried carrying around some of these bigger telescopes, you're going to do yourself in if you haven't got a mate. And I'm all alone on that desert island. So it's going to have to be a 10-inch or an 8-inch because otherwise I'm going to do my back in.
Okay.
Well, that makes sense, doesn't it? Because if you've got to travel from your home to somewhere to observe to get those dark skies.
From the cave to the beach,
Well, that's it. Yeah. From the cave to the beach. I was going to say that you'd need a car, but maybe you just have a cart or something. I don't know, on your desert island. But in the realistic world, you need to transport your telescope out to a dark site. So you want something that's small, compact, but will sit on the back seat of a car and not go out of collimation by the time you get to your observance site. Otherwise, you've got to then start collimating in the dark, which is downtime for your observing. So yeah, I go for the 8-inch apertures, the 200 mil, good aperture, good light bucket, and reasonable size. 8-inch f6 thereabouts.
Yeah, Lynn Talakalea in Hawaii. She's working at the observatories up there, and she says, Simon, come over there. We got plenty of large telescopes, and you haven't got to move them.
It's an island.
I'll take you up on that one.
That's it, yeah.
It's not a desert island, but it's an island, isn't it?
How come only Simon's getting the invites? What about me and Daz? We want to come as well. I should ask John. John, do you actually any observing through telescopes?
I've not done any for some time. I used to.
Yeah. What did you do? What did you have?
I got a 200 mil Newtonian.
Yeah, good. Yeah. Any particular favourite objects?
I like Andromeda.
Yeah, it is a thing, isn't it? You see the dust lanes. Yeah. But with Andromeda, there's so much to see in that galaxy.
Yeah.
You got M31, M32, and then you've got M110. Or NGC 205. So for the price of, for one object, you're actually getting 3 galaxies in that field of view. And how big is the Andromeda Galaxy to the human eye? If you could darken the sky, brighten up Andromeda Galaxy a little bit, it's 3 degrees, 6 full moon diameters in the sky. In a pair of binoculars in a dark sky, you can just get the hints of that. It's actually huge.
Some of the simulations of what Andromeda might look like as it gets closer to the Milky Way.
Oh yes, because we're getting closer. Yeah, I've noticed the difference over the last 60 years. Yeah,
that's a lovely picture. Pete, who took that?
Well, that's an interesting piece.
I wonder who took that.
Yeah.
Right, so in the centre we got M31, M32 is the little blobby one, and then just on the outer edge we got 25.
Yeah, you can tell that was Pete's. The sky's too dark.
Yeah. Well, an interesting image that myself and Rob Johnson, LAS member Rob Johnson, worked on. We took an image of the Andromeda Galaxy, M31, through a 12-inch Meade, and we actually worked out where the globular clusters are, because you got this halo, haven't you? Halo of globular clusters that surround the galaxy. and I think it's about 120 120 globular clusters around our galaxy. So we actually identified which ones were which, and referenced them all. And it's amazing what you can pick out just from from the city, a 30-second exposure, and you've not only got dust lanes, you've not only got 3 galaxies, you've got all these globular clusters in the field of view as well. M31, you're right, John, an amazing object. Yeah. Definitely a good one.
So, Daz, what's your favourite object?
Well, the Messiers. Well, I do really like the great globular cluster in Hercules. I really do like that. When you see a really well-defined image of that, it is really spectacular. But there are so many images just to choose from. When you've got the dumbbell as well, which is M27. I love the colors in the dumbbell. And you've got the Whirlpool, of course, the Whirlpool Galaxy.
M51,
again, that's another one. You get 2 for the price of 1 when you look at the wider view. So, yeah, there are so many things to choose from. To actually be asked to choose one is a little bit unfair, I think. But yeah, I do really like the dumbbell and the great globular cluster in Hercules. I do like that.
Dave,
Yeah,
you haven't answered your question. Answer your own question.
well, yeah, I've just I've got a list of globulars and galaxies and all Messier objects. And for those who don't know what the M number is, because we tend to just rattle these numbers off, don't we? We do our star, observing and outreach events. We go, oh, let's have a look at M1, let's have a look at M15 or M31, and people just think, well, are they playing bingo? Are they collecting motorways? What's going on out there? And for our listeners who have never come across these numbers before, these M numbers are part of a catalogue of deep sky objects, not all deep sky objects, as I should say, but certainly globulars and nebulas and a couple of galaxies. And it was from Charles Messier. And in 1764, he started collecting, basically collating a catalogue of fuzzy blobs that he kept coming across. He was a comet observer, and he kept coming across these fuzzy blobs time after time. So he thought, these are a bit of annoyance. I'll make a note of where they are in the sky, and then I'll know they're not comets. Now, Messier actually discovered something in the region of 13 comets, so he's actually got that to his credit. So he carried on doing this catalogue and ended up with 110 objects. He got about 41 objects that he actually put into the catalogue. And then there's a couple more added with a fellow astronomer. And then over the latter years, we ended up with 110. So it's now used. It's a bit of a Bible, really, isn't it? We have our NGC, the New Galactic Catalogue as well. Yeah. But the Messier Catalogue is the amateur astronomer's Bible.
Yeah, yeah. And he was known by the King of France as a ferreter of comets.
The comet, the ferret comets. So he was trying to not keep a come across these. Observe, these blobs as they were. So he ended up putting them all together. You've got M1, which is the Crab Nebula, a supernova remnant. M13, as you mentioned before, M13, the globular cluster in Hercules. But you've also got M15, which is a beautiful globular cluster in Pegasus. If you got dark skies, the Eagle Nebula, M16, looks amazing. Now, even in our light polluted skies, you can still see that. It's low down from the northwest and England, but nevertheless, you can use a filter, an oxygen filter, and it enhances that wavelength of light, and it jumps out, and there it is. It's just like those photographs, but in monochrome.
I mean,
so there's a heck of a lot.
Yeah, I mean, you also got your open clusters as well, and of course, the famous one is the M45, the Pleiades, which is beautiful. If you get that on
that's good for the wide field, isn't it? The low power wide field, whether it be binoculars, your eye. Yeah,
it is. There's so much in there. And as we were talking about earlier, if on certain times of the year, you can actually do what they call a Messier marathon.
That's
and basically that's where, if you get everything timed right, you can actually catch every Messier object in one night. It's a very long night.
You won't get it. You won't get them all in Shropshire.
No, Bath. You
M7,
can't get
M7,
there's one or two
yeah.
you can't get.
Yeah,
Yeah.
I must clarify that I'm talking about robotic.
Oh, cool.
Well, yeah, of course, you could do it robotic,
on
and you got
Slough, yeah.
access then around the
Yeah,
world.
on the
But-
Slough.
Yeah.
So you got the two, but it is a very long night. It's great fun. It takes a lot of planning, but they do quite often do it on. There's a robotics company called Slough, which is we do it on a regular basis. So yeah, it's a bit of fun. And as Dave said, it's the amateurs. It's what everybody starts with. That and then the Coldwell. Which of course was Mr. Patrick Moore. So it's what everybody looks for. It's got some of the best sights in the night sky. So yeah, it's what everyone starts with. But there are so many to choose from. To choose one is a bit of a hard task. So yeah.
Okay, Dave.
Well, there's so much of a variety, isn't there? As you say, yeah. Okay, Peter, are you done?
No, just move on to another question. We got 3 minutes.
Okay. Well, basically, it was a question, not so much a question, but of an observation there. SpaceX 9, the test launch in the last day, I think it was yesterday. They actually tested the engine 3 times in 4 hours. And it was quite, I mean, some may say it's like paint dry and watching paint dry, but you just didn't know what was going to happen. I actually had a point where I thought, I wonder if they're actually going to launch this and take it up to, a couple of, 40 miles or so, because the engine, they filled it up, they tested the engine, you saw the engine running, and then it just went quiet for an hour or two, and then you saw a little bit more of activity going on. The jets were coming out the side there, a bit of cooling, and then the engine done it again. And then Mr. Musk had tweeted that they're going to do a 3rd test. But that was a couple of hours later. I actually missed that one. I don't know did anyone see that? Simon's actually running a bit of video in the background on his screen.
That's all 3 tests.
Did you watch the 3rd?
Yeah, that's all 3 tests in this video.
And and they all worked okay, I assume. I didn't hear any negative reports.
No, although
I'm looking forward to that, going up and doing that backflip again.
They're not planning to launch until from the restrictions on from Monday onwards. So
right.
If they'd had a perfect, you might have thought, well, why haven't they launched you on a Thursday or a Friday? But maybe they have a few little niggles to get rid of.
Hey, Pete, can I leave you with a thought for the day?
Oh, of course, yeah.
Just going back to James Webb, people talk about the cost of this thing, 10, 11 billion dollars. To put that into perspective, given the universe is 13.8 billion years old or thereabouts, the cost of James Webb for looking back in space and time is less than $1 per light year. I think that's good value.
That's a bargain, that is, yeah.
That's excellent value. And on that, we'll be saying good night. And thank you to John for joining us tonight.
Thank you, John.
Thank you, Jeff.
But as I say, John, you're welcome to join the panel any night we're on. It's just an open link. You just join in and just join in the chat and whatever you want to do.
Yeah.
We'll be back on Monday with Reach Out and Touch Space. In the meantime, have a good evening or morning or wherever you are on the face of planet Earth, and even those that are beyond planet Earth, picking us up out there somewhere in space, aliens and stuff like that. We could be being picked up by aliens. Oh, mind you, you come to Oswestry, there's a few here.
Nanu.
So don't worry about it, aliens. You come here, you won't be out of place in Oswestry.
A couple on the panel here as well.
Come on the panel. I'm going to leave you with the travelling Wilburys, and I think this is something we need to do with the James Webb Telescope, and it's handled with care. Okay, folks, it's a wrap.
Excellent.